Good morning. I welcome you all back again after 10 days break. And we are now going to look at our handling dynamics with an additional design aspect of the vehicle, which we have not considered so far in our lateral dynamic study. So what is that we have not considered so far in our lateral dynamic study? Can anyone? Can anyone answer? What is that we have not counted, which is an important aspect in a vehicle in our lateral dynamic study?
Effect of suspension.
Effect of suspension. Good, Vineet. So, on today's class, particularly that we are going to look at what is the effect of suspension on our lateral dynamics. Right. So for that, before getting into that, let us just have an idea of what we have done in lateral dynamics so far, and then we will continue our class today. Maybe that would help you also that of a longer break. We will recapitulate what we were doing it in our lateral dynamic aspects. So we were primarily looking at a lateral dynamic study of our vehicle, considering 2-degree freedom model, what is called a bicycle model, right? In that bicycle model, the 2 degrees of freedom can be represented by lateral velocity and yaw velocity, or it can be lateral velocity and body slip angle at centroid. Body slip angle at centroid explicitly we have not looked at in the textbook because of the relationship between yaw velocity and body slip angle. You would be able to have body slip angle as one of the degree of freedom and work out. So which I would recommend that you can go through JASER textbook to look at it, because some of the journal paper, if you look at, you would see that they would consider yaw velocity and body slip angle as 2 degrees of freedom in their study, right? So one can do that also. And we were looking at so far without considering suspension, a rigid vehicle for lateral dynamic study. And that itself is quite sufficient in order to study or understand directional response and stability aspect of our vehicle. That's what we have understood. So what does that we have looked at in bicycle model? Bicycle model essentially whole vehicle weight is distributed in front axle and rear axle, and we had the collapsed wheels. Front axle 2 wheels collapsed as a single wheel, rear axle 2 wheels are collapsed as a single wheel, and we looked at the cornering stiffness of the tire and its influence. And in that also, importantly, we looked at the cornering stiffness value as a constant value, right? And we were able to define important parameters, something called what is called tire compliance. So the tire compliance in the front axle and tire compliance in the rear axle are defined by the terms exactly. What is the load, normal load in the front axle? You divide that by cornering stiffness of the tire. So what is that is called tire compliance. So you would have this compliance in front axle as well as in rear axle. If compliance is more in the front axle compared to that of rear axle, one can say that the vehicle behavior under steady state motion is understeer behavior. So you require to increase the steering angle according to the requirement of turning radius. So this is all something that you would understand, you have understood from the simple bicycle model. But today's class, we are going to look at the effect of suspension onto this vehicle model. We also have looked at with the bicycle model that stability analysis. So what is that stability that we were more looking at is yaw stability. So that is what is most of the time it happens because of the drifting of wheels in the axles. So the drifting can happen in the front axle where the rear axle wheels will be rotating, or it can happen in the other way. Rear axle wheels will be drifting and the front axle wheels may rotate. So that would essentially respectively would explain the phenomena of vehicle tendency understeer or oversteer. And if it happens that vehicle speed is of critical speed that we have studied, and your understeer gradient for your vehicle is negative value, then obviously your vehicle would go to an unstable state and steering is no more possible. The requirement of steering, you can reduce it by counter steer if your vehicle speed is not reached to the critical speed. But at critical speed, even though you are trying to exercise your steering, you cannot, the driver cannot do an steering control, and control of steering is lost, and the stability of your vehicle is lost in the yaw plane. That means the vehicle would be spinning about on Z axis. So that is what is that we see yaw motion, unstable state of your vehicle. So this is all we have seen, and today's class I am going to explain you the effect of suspension onto your vehicle. So what are that we are going to see is today's class we are going to look at its yaw stability point of view, or yaw motion point of view, directional control and yaw motion point of view. In additionally accounting the suspension. If we are also looking at the stability analysis of your suspension, what would happen? Stability analysis of a vehicle, consideration with the suspension, you can have a phenomena called rollover stability, right? Which is the roll of your vehicle, or toppling of your vehicle with respect to roll of your vehicle about a longitudinal axis. That is also will make your vehicle to go in an unstable state, which is not possible to explain its physics through a 2-degree freedom bicycle model, what we have considered so far. So in order to understand the directional response of your vehicle, as well as the rollover stability of your vehicle, we have to account the important design aspect in your vehicle called the suspension system of your vehicle. So similarly, there are other design aspects of your vehicle which can give an influence of lateral force that is necessarily to be generated for your lateral dynamic motion. Would also have an influence on this understeer gradient. So we are going to look at all of them in our subsequent classes. And today's class, we are going to take an important aspect of suspension design and its effect on the lateral dynamics of your vehicle. So let me share my Active Inspire board to begin our class. Hope you are able to see this. Today's lecture is lecture number 37. And today's date 12th May 2021. So today's topic of our lecture is effect of suspension on cornering. Effect of suspension on cornering. Okay. So let us understand an important definition called the static margin. So the static margin I'm going to define in order to understand the vehicle tendency when there is a side force that is acting on a vehicle. So you know what is steady state yaw velocity. So what do you mean by steady state yaw velocity? Yaw is the motion of your vehicle with respect to vertical axis. So the orientation change of your vehicle with respect to vertical axis is what is defined the yaw motion. So the rate at which that angular increment orientation change is what is defining yaw velocity. So steady state yaw velocity means the yaw velocity is constant. Yeah, acceleration is zero. That's how you understand. So when vehicle is undergoing a steady state motion, the steady state yaw velocity when it is undergoing a motion you see there is a side force that acts on a vehicle. So let us look at a vehicle. We can consider this as your simple passenger car. And I have here the CG location of the vehicle, and you know this is wheelbase L, and the distance of CG from front axle is A, and distance from rear axle is B. So if that is so, you see that this, how do you define the static margin as? It is the ratio E by L. So what is this E by L? So E is the distance from CG, a point, what is called a neutral steer point. So this point is what is called a neutral steer point. So what is neutral steer point? How do you understand neutral steer point? Neutral steer point is the point where when there is a side force is acting on the vehicle will not produce steady state yaw velocity. That is how you should understand. So if a vehicle goes straight in a highway and there is a side force acting, and the side force is acting at a point in a vehicle, its resultant at a point in a vehicle will not produce any yaw velocity, steady state yaw velocity. At that point is what is called a neutral steer point. And this neutral steer point can be in a vehicle behind the CG location. So this is CG. This is CG. It can be behind the CG location, or it can be in front of the CG location, or this can also coincide with the CG location. So now, what is this point is called a neutral steer point, and this point can have a variation, and that would have its position changes in this line called the neutral steer line. This is called neutral steer line. So in a neutral steer line, you'll have a point called a neutral steer point. If the side force resultant acting at this point will not produce any yaw motion, will not produce any steady state yaw motion. There is no orientation change that would happen. So that is the point. So you understand that, right? So I drive my vehicle straight. There is a wind gust at the side. The resultant of that act on a vehicle, but still my vehicle go in a straight path without any angular orientation change with respect to vertical axis. That is what is called a neutral steer point. And that neutral steer point would happen behind the CG, then it is under steer effect. So this neutral steer or the static margin value can be positive value or can be negative value, can also be zero value. Zero value. So when this E by L is positive value, then it is referring to an understeer tendency of the vehicle. When it is equal to, when it has a value, negative value, then it is referring to an oversteered tendency of the vehicle. When it is negative, when it is in front of CG, then it is oversteer. And it is zero, that means neutral steer point coincide with the CG location. Then it is called a neutral steer point. So E by L is zero, then it is neutral steer point. So for a typical vehicle, if you look at this E by L value would be this ratio. It's normalized by the wheelbase. E is the distance from here. So this is the distance E. So this E divided by L is what is normalized, and that I call it as a static margin. And if that value would be typically for a vehicle 0.05 to 0.07, it would be generally. So why is it considered is because in a see now there is no roll, there is no yaw motion. It is a vehicle when you consider this neutral steer point. So is a point when the side force cannot produce or is not producing any yaw motion. That is how you define. The similar analogous definition is what is important in our suspension when you account called roll center. We will see that in a while. So beforehand, you can derive this expression of E by L as this. So what is this you have to consider is this E position, where is it located? Let us say that is from the front axle at a distance A N. So A subscript N refer to neutral steer point position from the front axle. You will have from here to this rear axle, it is length L. So now you can define your E by L or this distance AN. Where is this neutral steer axis? AN you can calculate and find whether it is going to have positive value or negative value, or AN is equal to A. This can be determined simply from the definition of neutral steer tendency. So what is neutral steer tendency? QUS is 0 at neutral steer tendency of the vehicle. So if KES is 0, how do you define this? KES is also defined from a stability factor. We have looked at there is a relationship between that. So what is how do you define stability factor? From your characteristic equation, you are able to get that by applying Rao's stability criterion there. So that is M into BC alpha R minus AC alpha F by L squared C alpha F and C alpha R. So this is what you have written. So when KES is 0, what do you mean by that? K3 is 0. Other way of telling. So when I say that, it is going to be BC alpha minus AC alpha F, BC alpha R minus AC alpha R is alpha F is equal to 0. So that will result in the ratio of B by C alpha F is equal to A by C alpha R. And what is B now? What is B now with respect to neutral steer point? It is AN. So B is AN minus L, because to get what is this AN. So AN minus L by C alpha R is what is equal to A by, sorry, AN. B is this distance. This distance. So this is AN by C alpha R. B by C alpha F. This is. So you are able to define now what is this distance AN. So let us take from this. This is not AN minus L. This L minus AN. It is correct there. This is L minus AN by C alpha F. So from this L by C alpha F would be, if I take it on this side, it is going to be AN is taken out. It's 1 by C alpha F plus 1 by C alpha R. So this is going to become, I require AN. So AN would be, take LCM here and then take this up. So you will have AN as L into C alpha R by C alpha F plus C alpha R. So you are given a vehicle with the wheel base and your tire cornering stiffness of the front axle wheels and rear axle wheels are assumed to be constant values you are having in your hand. You can just calculate this and you will have AN. If AN is greater than A, so what do you mean by that? You have your static margin positive. If AN is less than A, then you will have static margin negative. So based on that, you would be able to say whether vehicle is having understeer tendency or oversteer tendency, right? So this is how you can find this. So now what is this distance E? is AN minus A. If AN is greater than A, it is positive. If AN is less than A, it is negative, right? So this is simple understanding of static margin. When you are saying that you are looking at yaw motion of your vehicle, this is an important definition which we have not talked in our previous lecture. So I just wanted to tell this, and then we will proceed with now this suspension effect on cornering, right? So let's look at now an important, see, so far in our bicycle model, we have not considered suspension, which I was telling you at the beginning of the lecture as well. And we were looking at importantly a definition called cornering. What is that? Is compliance. Compliance. Cornering compliance. So that is defined by degree per G. Right? Degree per G. And this was only considered for our vehicle, and the vehicle is assumed to be a rigid vehicle. Now the vehicle mass is discretized because of the suspension taken into account as unsprung mass and sprung mass. So unsprung mass are the mass that include all the masses of the elements of wheels, axle, anything below the suspension available in the vehicle. Anything above the suspension, your vehicle body and all inclusive of vehicle body, all are called sprung mass. So since there is suspension considered, now the vehicle is not called a rigid vehicle, it is flexible vehicle. And as we are aware that the CG location is elevated from the ground, there can be a chance of lateral load transfer as suspension now is coming and dividing the entire vehicle mass into two masses. Right, so that's what we are going to look at it. And before that, let's also understand an important definition for understeer oversteer, once again called Olley's definition for understeer and oversteer tendency of the vehicle. So how do you represent that is if you look at from the top your vehicle, which is again our skeleton, where this is front axle and this is rear axle of the vehicle. And if vehicle is of neutral steer effect, the vehicle motion is at an angle or in straight path like this. This is the path. If it is neutral steer vehicle, it will go in this path. When there is a side force that act at the CG location, this is the CG location in the top view, and there's a side force here, say Fs, acting at CG. If this goes in straight line, then it is of neutral steer tendency. At that time, the static margin is 0, right? Static margin E by L is equal to 0. That's neutral steer tendency, yeah. And if it happens that if the vehicle tendency is of understeer tendency, the path will be like this. For understeer tendency, if it is of oversteer tendency, this would be the path, right? There are 3 cases. So if E by L is greater than 0, right? That is positive value. If it is positive, then it is of understeer tendency of the vehicle. So what do you mean by understeer tendency of the vehicle? See, you would have your side force acting at CG, but your neutral steer point is somewhere here, right? That is the meaning. This is at a distance E. It is here. This is neutral steer point, and this is your CG location. This is your neutral steer point, NSP, say. So since it is now ahead of this, if this Fs is acting at this neutral steer point, there is no effect on the yaw motion. That's the meaning of neutral steer point. But the side forces act at the CG location and neutral steer point is here. So that would create a moment in this sense, in the top view. So that is the reason why you have your understeer path is going away like this. If this is the straight motion and you have side force, and the vehicle will turn away from the disturbance force. If it is another way, E by L value is less than 0. That means it is negative and you have your oversteer tendency. That means what you in the other case, let me put that with the red color, I will have my neutral steer point here and E is from here, it's measured. And you see this force which is acting at CG would create a yaw moment in the sense that the vehicle would come inside of the on the side of the disturbance. That is what is oversteer tendency. So you would connect that static margin definition with reference to this Olley's definition for understeer and oversteer tendency. Right. So this is what is with the understanding. Let us now look at what is the influence of suspension on lateral dynamic aspect. So for that to understand, we need to understand importantly roll moment distribution. Roll moment distribution, right? So what do you mean by roll moment distribution? The roll is the motion of your vehicle with reference to your longitudinal axle, right? So you see that as you take a turn towards right, you would have your lateral load transfer from inward to the outward side. So the roll will take against that of a turn. Right. So what would happen if that rolls like that? The entire weight of the vehicle, which is balanced equally before the turn on by both sides of the wheels, now would have more normal load on outer wheel compared to that of inner wheel. So this is going to create a distribution of roll moment in the front axle as well as in the rear axle. So this roll moment distribution happens to be more in the front axle compared to that of the rear axle. The vehicle tendency would be understeer tendency. If the roll moment distribution is more in the rear compared to that of the front, then the vehicle tendency would be oversteer tendency. Because this roll moment is going to be straight away connected to lateral force, vertical load, and the slip angle in the front axle and the roll angle. So these all are something that we are going to connect them when you look at the free body diagram of a vehicle model to account the suspension effect. Right. So let me draw the free body diagram and go ahead with our class today. So let me consider a flat surface, right? And I'm going to consider an axle now. And this axle is collapsed of front and rear axle together, like that you can imagine. So I'm taking a plane section of my vehicle along the CG. I know that it doesn't count the front axle as the rear axis. I consider a plane. What is that plane? Y is that plane passes through CG. And I'm going to draw this simple schematic representation of my vehicle, considering an equivalent springs, all four springs of the vehicle into two single springs, equivalent springs. And this is what is the separation distance of the spring, say S. So some of the time rear axle will be solid axle, front axle will be with the independent suspension system. then you may consider this separation distance as same as that of the distance between the wheel contact point. So generally we call this distance as tread or track, defined by small letter t. That is called tread or track. And the separation distance here for the spring, let us consider this distance as s, right? So now over which I have my vehicle, and that vehicle is defined comfortably like this by the mass. So this is my simple schematic representation. And the elevated vehicle here, so I would have the CG location not very close to the ground. It would be at some height, and let us say somewhere here I have my CG location of my vehicle. This is my CG location of my vehicle. So now what would be my free body diagram if this is stationary vehicle or it is going in straight path? I would have here now F is at, so I would have here, so there will be F is at here and F is at here, and there will be weight from here, right? So this is a simple free body diagram. I'm not drawing free body diagram sprung mass separately and sprung mass separately. I'm drawing whole vehicle is described by now an equivalent springs carrying sprung mass and the other end of the spring connected to the axles. So these axles are the front axle, rear axle collapsed and I have. So each side you can consider the wheels are two wheels together like that, right? So if this is that is the state of free body diagram. If the vehicle goes straight or it is stationary, right? And the springs are sprung and there will be a static deflection of the spring at that moment. So now if I take a turn on this side, if I take a turn like this, so what would be my free body diagram? Look at it. So I have a ground and this wheel, and there will be small angular rotation of this axle, very small, right? And then I would also have here this, since it is taking a turn here, the load transfer from my right to the left like that. So the vehicle sprung mass would have rolled by an angle like this, and this side spring would be like this, and this side spring would be like this. And it is about the mean position, right? So now you know the equivalent stiffness of my springs here is Ks, spring stiffness, and there is something called for a whole vehicle suspension roll stiffness. Roll stiffness called K subscript phi. Why subscript phi is because phi is what is a roll, right? Phi is what is the roll with respect to longitudinal axis or x-axis. You know that. So K phi refer to roll stiffness of my vehicle, right? So now just let us look at what is that free body diagram now going to be. I have here F is at, and I will call this F is at now with the subscript naught, F is at naught, outer side normal, and I would have here F is at I. If you see this length is smaller than that of this length, so this is longer because the load transfer on this side. The magnitude on the outer normal load is more than that of inner normal load. It is equal otherwise if it is not taking a turn. And now what would be the location of my CG? Location of my CG would be now, if this is the vertical drawn, and it would be somewhere here, and I would have now this height of my, this is height of CG from the ground would be now described by two heights, right? One is in between a point called roll center RC. So the height of this roll center given by HR, and from here this remaining one is H1, 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 right? So now there is a point called roll center. What is that point refer to? The roll center is the point that would transfer the lateral force to the sprung mass. So if I say that, you are very clear that if, let me just erase this arc to avoid confusion, right? So you know that it takes a right turn, and this is a free body diagram. And since it is taking a turn like that, it taking a turn to the right, I would have my lateral force developed would be directed to the right. So the distribution of this lateral force is same as that of the distribution of normal loads of the vehicle. So here you see this with the same proportion. It would be a proportion to that. So Fyi, this is Fy naught. Fii, Fi naught. And the resultant of these two, sum of these two, Fy would be transferred to the sprung mass to the CG location, transferred to the sprung mass through the point called RC. That's the point called RC. So let me just explain you that transfer alone with respect to these lines. So just to see that on this line, I would have force Fy, which would be equal to Fy naught plus Fyi. And this force would be transferred now through this point roll center, which is placed at a distance from the ground, HR. So this Fy would be transferred there, and you can cancel it like this for an equivalent system. So now you see that this and this create a couple, and that couple is responsible for the roll of this axle. So as the lateral force transferred to the sprung mass, it would create an instantaneous effect on the axle, and that would have a smaller roll effect of the axle. And now my Fy is at RC location. So this is my roll center location. From there to CG, here, this can be transferred. So this is taken as it is with this, and cancel this. So it is an equivalence. So this now goes off. These two goes off. Right. So these two now form a couple, and that would be the couple that is responsible for rotating the sprung mass. And this Fy is left now, which is now a lateral force that is acting effectively transferred from the road to this point. So the Fy which is developed at the contact patch is getting transferred to the CG location of the vehicle, and that would be equal to centripetal force by Newton's law. Otherwise, I would say that as a dynamic equivalent system in the same free body diagram by representing the D'Alembert's force, centrifugal force. So what is that force quantified? That would be quantified by W U square, where U is the forward velocity, squared by RG. So this is what is now the force at CG location, and as well as the weight would be acting down now for this vehicle here, W. And if you look at this entire configuration change, it would be now like this. So this vertical, so there will be a roll. So this angle here, is what is an angle phi. This angle here is that is an angle phi, right? Role of this. So the role of sprung mass is independent of role of the axle. That is what you have to understand. So there are, so what is essentially happening when you take a turn to the right? There is a load transfer from inward to the outward. So that load transfer is what is called a lateral load transfer, and that arises with two important mechanisms. So that one to understand, let us write down this equilibrium equation. So now this is my free body diagram. So weight at CG location and centrifugal force, that's D'Alembert's force. And there are two couples which is not appearing here. I don't put that explicitly here, as there is a role that takes place, that's changed. So this, whatever this role of the sprung mass would be resisted by the spring roll stiffness. So roll stiffness into roll, K phi into phi is what is the roll that is resisting the roll of the sprung mass. So this is all to understand. Let us now put down by the equation. So you can also look at this angle phi here. You can also look at that angle phi to the horizontal here. So this is the role of your vehicle body, right? So this is that free body diagram. So now let us write down this equation. So what is the first equation? First equation is in y direction, sigma Fy equals 0 when I write. That's very clear. Fy naught plus Fyi, which is total Fy, and that would be equal to W u squared by GR. Because this sum is what is balanced by this, right? That is there here. And you should see that the role of this takes place because of transfer of lateral force to the CG location, right? And that is by these couples. So there is one couple here, there is a second couple here. So this forms a couple and this forms a couple. Both make them to roll outward of the turn. That's very important. So my turn is in this direction. Turn is in this direction. It is going like this vehicle. And this is the free body diagram. Right? So this is first equation one. What is my second equation? This Fy, whatever is there here, into H1 is what is equal to this Fy into H1 is what is equal to K phi into phi. So let's have this as the second equation. What is K phi is roll stiffness. How do you get to your roll stiffness of the vehicle? That roll stiffness K phi can be obtained in terms of spring vertical stiffness Ks, and that would be half into Ks into S square, where S is the separation distance of these springs. So this can be easily proved by looking at with respect to static equilibrium position. If you look at here, there is a spring force. I don't show the spring force here because I don't cut the springs. So whenever you draw the free body diagram, the constraints when you are removing, I remove the road, I show my Fz and Fy, right, like that. I do not cut the spring, so I don't show explicitly the spring force here. So the spring force now on this side will be pulling down, and this side, this side it will be pushing, and this side it will be pushing down. So that Fs into this distance, separation distance S, is what is equal to K phi into phi if you use, and you see that the deformation in the spring would be delta Fz by 2, where delta Fz is change in the normal. If you consider, you can have this relation. So I leave it to you to just to work out this relationship. This is very simple. You can just work out. In case you do not get, I'll explain you later. So these two equation, and this is the relationship between roll stiffness in terms of vertical stiffness of my spring. And my third equation is, let me take moment balance or moment equilibrium at roll center, considering counterclockwise moment in this picture is positive. So if I do that, I have in this free body diagram, what are the forces? Just look at them. So I have these are the forces. So here this distance is t. So let me write down that equation here. So that is minus Fz naught into t by 2. So I consider this approximately at the distance. There is a small roll, but these angles are very small, so I can neglect. I can consider still it is separated by t by 2 and t by 2. So Fz naught into t by 2 is what is clockwise moment with respect to this. So minus plus Fz I into t by 2 is positive moment. And I have this Fi naught plus Fi. So the sum is what is Fi. So let me take that as from here Fi into HR, the distance HR. And that moment would be counterclockwise moment. That is why I have here plus moment. And the moment by Fy. So Fy, where is it acting now? Fy is acting to the, this is Fy. So whatever is there here, this is Fy. So this is Fy into this distance. So that would be Fy into Fy into H1, because I take moment about roll center. So this Fy into H1, this height distance I take. Of course, you can ask that the cos theta, if the angle is very small, cos 0 is 1. So I don't consider that here now. So this all when it is all when you have this picture transformed to this instantly. So this picture is going straight, and when you're taking a right turn, immediately there is a roll, and this is the free body diagram. There is slight roll of your body, and you get your CG is slightly moving away from the vertical, and hence this free body diagram. So when I put the dynamic equilibrium, I would have my simple moment equation equating to 0 here now. So this would be again rewritten as Fz naught. I take these two terms on the other side minus Fz I, and the remaining term here, that's going to be 2Fy into HR by T plus 2Fy into H1 by T. So this difference here, Fz naught minus Fzi is delta Fz. So this delta Fz is for pair of wheels, so that you have to remember this. So there would be some confusion. Sometime it is on one axle or it is both, consider, right? So this is Fz change in normal load. That would be equal to 2Fy into HR by T plus 2. This we can look at it from equation 2. So this is equation 3. From equation 2, I can replace this Fi into H1 by this K phi into phi by T. This is my equation 4. So now, see, there are two mechanisms that are very evident here for lateral load transfers. Due to this lateral load transfer arises from the two mechanisms. What are the two mechanisms? Here, one is the first term, 2Fy HR by T. And this is lateral load transfer due to cornering forces. This is lateral load transfer due to cornering forces. And the second mechanism is purely by roll of your vehicle. So this is lateral load transfer LLT due to vehicle roll. vehicle roll. Right. So let us understand these two terms refer to two different mechanisms. So what are the significance of these mechanisms, and what is that you have to also critically look at it is it is independent of roll angle. So if you look at here, this first mechanism, there is no roll angle comes. So the lateral load transfer due to cornering force is independent of roll angle of the body and the roll moment distribution as well, right? Whereas if you look at the second mechanism of lateral load transfer due to vehicle roll, it depends upon the roll dynamic aspect of your vehicle. That means the property of your springs. So the cornering condition would change this value. So it is directly dependent on the front or rear roll moment distribution. So this second term is depends on roll moment distribution. So this term depends on roll moment distribution in the front and rear axle. So you have to understand this roll moment distribution. For that, the free body diagram that we have drawn to understand the two mechanisms that happens because of that influences the lateral load transfer. Two mechanisms, reason for the lateral load transfer. One is independent of roll. Another one is depends on the roll and the roll moment distribution. So to understand this roll and roll moment distribution, I have to consider my all the four wheels and full vehicle free body diagram. And that I am going to do in the next class and complete the remaining part of the derivation. Also, let us look at additionally other design aspects like camber and lateral load compliant steer effect. What do you mean by that? There are some more effect are there. That all we will see. This roll happens in the vehicle would also induce a roll steer. That's something that we have discussed. So what would be its effect? Like there are some understeer influence. There are influencing factor of this understeer gradient, which we have looked at, and we will see them also in the forthcoming classes. And then we will do rollover stability analysis, and that completes the fifth module. Then we will enter into vertical dynamics aspect of our course. So with that, I'll complete today's class, and we'll again meet on the next class. If there is no class on this when Friday, then we will meet on Monday, right? Yeah. And your J component draft papers that I keep receiving now, there are few students groups are to request some time can take and submit it. And I would address that whatever you have submitted, my remarks and comments in the coming weeks. I would call group wise. As I finish and I have completed your review, I'll call group wise and I'll take your review. So those who are not finished, you can keep working on it. Those who are semi-finished, there are students who have finished only some part and submitted. So you can rework on it. However, whatever that you have mailed to me, I will go through, and we will have in the coming week and the following week, we will have a review, and that review would help you to further fine tune, convert that as a submissible. You can submit that to a journal paper or at least to the conference. So we will bring to that state, and then we will have your final review the last week of our semester. That would be the first week of June. Or 2 days, I just make you all to present comprehensively through a poster where you can bring in all those important aspects of your J component work into a single page, and you can present. So that is that action plan for the coming weeks. So we have our classes till 8th of June. And before that, we will have to complete a lot many aspects. Right, as that note, let me just stop today's class. And if you have any thing to ask, you can go ahead asking. So you have anything to ask? Otherwise, I will stop at this point of time. I download the attendance and stop today's class.